Hello, my name is Brock Parker, and I'm a sophomore here at UW studying astronomy and astrophysics. My research group is headed by Professor Chip Kobelnicki, and we are working on confirming exoplanets from NASA's Transiting Exoplanet Survey satellite. Now, what do we mean when we say transiting exoplanet? Well, a transit is when a planet or some other object passes in front of a star. So over here we can see Venus transiting in front of our Sun. And an exoplanet is a planet that is outside of our solar system. So a transiting exoplanet is a planet outside of our solar system that passes in front of its star, blocking some of the light. Now, why are we researching these exoplanets? Why are we looking for these exoplanets? Well, as astronomers, we know a lot about our solar system and how the planets formed. What we don't know, however, is if our solar system is unique. So we are looking to classify and describe these exoplanets to see if they are similar to our solar system or wildly different. So how do we go about finding these exoplanets? Well, we use the transit method. When this opaque planet passes in front of the star, it blocks some of the light, resulting in a dip in the brightness. And so when we measure the brightness over time, we see this dip. And the depth of this dip is equal to the radius of the planet divided by the radius of the star squared. So when we have a smaller star, such as this, we see a greater dip. And some other things can affect the depth of this dip as well. If the planet has an atmosphere, in certain filters you'll see a bigger radius and a greater dip, because the atmosphere will block the light in that wavelength, in that filter, but not in the other filters. So what do we expect to find when we measure these light curves, when we measure these dips? Well, we expect to find light curves that look very similar to the ones in those first images, where you have a nice flat bottom or maybe a slightly rounded bottom. However, there are other types of light curves, and they mean different things. For example, this V-shaped light curve indicates a grazing transit, where instead of the planet passing all the way in front of its star, it just grazes the corner, and so you don't get that bottom where the planet is constantly in front of the star. You just get this very bottom part where most of the planet is in front of the star. Also, you can see light curves that look like this, with two different dips of different depths. And that is an indicator of eclipsing binaries, where one star will pass in front of the other, and depending on the brightness of the star that is eclipsing the other star, that'll determine the depth of your dip. So when the dimmer star eclipses the bright star, you get these bigger dips, and when the bright star eclipses the dimmer star, you get these smaller dips. However, for the most part, we don't expect to find any of these. Now, how do we pick our targets? We are following up on TESS, which is NASA's Transiting Exoplanet Survey satellite. TESS is a successor to Kepler in that it is looking for transits all across the night sky, approximately 85% of the night sky. It does this by selecting regions of the night sky and observing them for 30-day consecutive periods. Scientists will then go and look for these light curve dips in these stars and report any findings they have. We can then take these findings and their parameters that come with it and pick our targets. So there's a few required parameters that we have for our targets here at WRO. For example, we have a required depth of around 1 part per thousand, such that we can overcome our signal to noise and get good lossless data. As well, we have to have stars that are bright enough to get enough photons in a certain amount of time to make accurate observations, which comes out to about 12th magnitude stars. Also, our survey, our follow-up, focuses more on hot Jupiters, so we focus our target picking on these hot Jupiters. Once we pick our targets, we then have to figure out when we can observe them and their observability. And this observability depends on two different parameters, the transit timing and the visibility. The visibility is just whether or not we can see it at night, how high in the night sky it is. And that's what this black line here over on this curve is. This black curve over here on this plot is the height of the target over the course of the night. We then have to know when the transit occurs, the transit timing. And we can do this by using the last known occurrence of the transit and a known period and calculate when the transit occurs. And when these two line up, we get plots that look like this. These are plotted in Python, and this gray rectangle is our transit timing, so it's about 4 to 8. And this black curve is our target. And so we can see they line up, and we can observe it from evening twilight to morning twilight. So most of it is within those bounds, and this is a good night to observe. So when we go to observe, we use WIRO, the Wyoming Infrared Observatory, which is a 2.3 meter Cassegrain telescope located on Mount Jelm, approximately 25 miles southwest of Laramie. Now, Wyoming uses a double prime diffuser for its observations, and this means that double prime is just the type of camera and focus which ends up resulting in a 4096 by 4096 quad amplifier readout, and that just means that each one of the quadrants of the picture has a different light sensitivity. This diffuser takes the focus point brightness of the star and spreads it out over a greater area such that we can take longer exposures and not overload our sensors, and this is called the point spread function of the star. We observe these stars in the G, I, R, and U filters. When we observe these stars, we get pictures that look like this over here on the left. Here's our target star, TOI 1181, and then we have these other stars, and you can see the point spread function where they're spread out over a circle. We can then use this and some other resources to pick our comparison stars, which are these stars here in red. This T1 is our target, these are our comparison stars. Comparison stars have three properties we're looking for. We're looking for nearness to the target star, so this one's very close. We're looking for brightness, so once again this one is very close, this one is very bright. And we're looking for similar temperatures. And this allows us to normalize the data. What do I mean by normalizing the data? Well, we are looking to measure how the star, the brightness of the star, changes as compared to the rest of the sky. But first, we have to get rid of some of our biases and our flat fields. So as I mentioned earlier, each one of those quadrants has a different sensitivity to light, which means that we can measure the sensitivity by closing the shutters and just taking a raw picture of the black and measuring just sensitivity. We can then divide this out to get a normalized image with the bias taken out. We can also then check for bad pixels by taking flat fields. So flat fields are just pictures of the night sky where there are no stars, nothing to be observed, just a flat picture. And we can then average them together and also divide them out using IRAF. And IRAF is a Linux program that allows us to do pixel by pixel analysis of these images. There's also the dark current, but for WIRO the dark current is negligible, so we ignore it. We can then import this biased and flat fielded data into AIJ. When we import it into AIJ, we are looking to create this curve fit. And as I mentioned earlier, we're also looking to normalize these brightnesses. And so we are trying to compare the brightness of the star to the rest of the stars, because if we have a cloud pass overhead, obviously the brightness of all the stars are going to decrease. But we are looking for how the brightness of the main star decreases as opposed to the rest of the stars, not the whole field. So we try to get rid of this overall changing in brightness throughout the entire night. And we do that using the comparison stars. Once we do that, we get a curve fit with parameters that look like this. For this fit, we are trying to minimize the error, which in this case is measured by the root mean squared RMS of the fit. And when we minimize it, we will get our planetary parameters. Now, the planetary parameter we are most concerned with is the radius of the planet. And once we do it, we get graphs that look like this. This blue curve here is the fit of the data. The blue dots are the data. These blue dots up here are our residuals, which you can see are very small, which indicate a good fit. This is a plot of TOI 1181 on the night of July 6th, 2020. We are missing the ingress of this plot, but we still get a good fit. We can also then take that and compare it with other nights of data. So here we have 815, 617, and 617, 617. These are in the U filter, R filter, I filter, and G filter. And all these nights of data together tell us that this is a pretty good fit and a pretty convincing candidate for a planet. We don't see any abnormalities in the fit, and we just see a little bit of an offset that is consistent throughout. So we don't see transit timing differences. So what can we conclude? We can then, from this data, conclude that TOI 1181.01 is most likely a planet, and it is a planet with a radius of about 1.5 times that of Jupiter. Now, we still need to do better on our fits. We need to more precisely compute these parameters, and we can do that using an MCMC fitting program, such as ExoFast. And once we do that, we can get more accurate values of this radius. As well, we're looking to take more observations using the Red Buttes Observatory, which is another 0.8 meter Wyoming-owned telescope south of Laramie. We're going to be taking observations on TOI 1181 plus some of our other targets, and hopefully we can confirm and classify more of these targets. Thank you for your time. Let me know if you have any questions.